Welcome to this first afternoon of Vox Days Belgrade. I hope you're enjoying the conference. You have arrived to watch the myth of the magical messaging fabric. Yay! My goal today is to become one of the top 4 presentations because all of them were around soft skills. So I'm going to prove that a properly technical presentation, sort of, can also be quite entertaining. So who am I? This is an excellent question. My name is Jakub Korab, or Jakub Korab, because we're in Eastern Europe and I can pronounce my name correctly. I am an independent consultant working in integration and messaging. I usually put out fires. So people call me when nothing is going right and they need some help desperately. So this is where I am. And I have worked with close to 100 companies at this stage over a 5-year period. So I like to think that I've seen a few things. So one of the things that I have noticed in all of my travels as I have meandered around Europe is that companies tend to jump around between products if they don't work the first time. Does this sound in any way familiar? Yeah? Okay. So in doing so, they trade one set of problems for a completely different set of problems that they didn't have with the other product. So with what I'm going to talk about today, I'm going to talk about how we get these ideas in our heads by talking about messaging. But before we do, let's talk about myths. What is a myth? People conventionally think of a myth as being by this particular definition. It's an idea or story that is believed by many people, but that is not true. Fair enough. I don't particularly like this definition because it oversimplifies something which is actually quite useful. It's also quite dismissive of the purpose of what myths actually serve. I prefer this definition. A myth is a usually traditional story of semi-historical events that unfolds part of the worldview of a people or explains a practice or a belief. So myths are stories about our world that guide us. They're partially informed by experience, partially through that of others. And it's the usefulness of this guidance as to why we as humans have always told myths. Because they hold a grain of truth to them that fill in the gaps of our experience. So let's talk about mythology. Well, mythology comes from 2 root words, which are different modes of thinking. The first one is mythos. Mythos approaches the world through indirect, intuitive means. Through it, we discover things that are subjective, based on individual feelings and experiences. Logos, on the other hand, approaches the world scientifically and empirically. It looks through guidance, guided by things that you can prove through facts, through experiments, through deduction. So we look through truth via logos that is objective and universal. So for this you need time, experiments, and maybe to read the documentation. So with only partial grasp on objective truth, we fill the gaps with mythos, like the blind men feeling an elephant. Oh, this kind of feels like a snake. Oh, this kind of feels like a tree. We fill in the gaps with mythos. And in IT, we're not immune to this. We have answers from Stack Overflow to the wrong questions. We have half-read tech articles. And we get glossy conference presentations from vendors. So let's demystify an area that I'm personally quite involved in, which is messaging, which is the movement of data between systems through the use of an intermediary. Now, messaging is not glamorous. It's half-jokingly referred to as plumbing. And that's unfortunate because plumbing is integral to so many different things that we do. Am I right? Okay, so I'll get everyone in the room to stand up, please. It's better than raising hands. You people in the back of the room, I can see you not standing up. You too. Stand up, stand up, stand up. So sit down if you don't use messaging at all. There's like one guy who's sat down, and I'm pretty sure he's just bored or something already. So sit down, sit down. Okay. So it's used absolutely everywhere. So we all have limited time and attention. Okay? And in an industry that's as fashion-driven as ours, where everything superficially seems to be moving so rapidly, Docker containers, Kubernetes, Mesos, da-da, people often focus on the shiny technologies, as you do. Partially because they're cool, because everyone likes to deal with, fun stuff, and partially through the fear of being left behind. And in doing so, we leave behind the things that are most ordinary, which don't necessarily, as a result, get the attention that they deserve. And so we forget they're there while we're busy dealing with other things. The people who looked in detail at what these systems did, how they work, they move on, and we're left with gaps in our knowledge and half-remembered stories, myths, about what to expect from them. So what sorts of stories do we tell ourselves? Well, it's not uncommon to hear things like, we will never lose messages. Messages will be processed in order. At this point in time, you're thinking, hang on a second, this is actually, there's nothing controversial about this. Adding consumers will make the system go faster. Messages will be delivered once and only once. Some people are starting to sweat already. And we should just be able to add this extra million messages a day and everything's going to be fine. And it all comes from one statement above all else which creates this situation. It's just the pipe. For a lot of people, this is where the hand-waving starts. Yeah, it just does this, it's fine, it's whatever. But if you look closely as to what exactly is going on here, you'll see that there's a lot of stuff actually happening inside this pipe, and it's a lot more than meets the eye. So by telling these stories, we transform something that is everyday and functional into a thing with wondrous properties. Inevitably, later on, typically in production, we are disappointed with the results. To get past this state, we need to get a better understanding of what exactly it is that we're dealing with. So whether a messaging system can address your use cases and how it goes about doing it depends on its underlying design and the trade-offs that its authors originally chose to make. Sometimes they're obvious. Other times you need to get a deeper understanding of what exactly is going on, which means drilling beyond the front page of the documentation and a couple of glossy conference presentations. So today, what I'm going to do is I'm going to talk to you about two products, ActiveMQ and Kafka. They superficially play in the same space, the distribution of messages between systems. However, they have deep differences in approach and target use cases. The goal of this isn't to explain these two products to you in detail, because that's not possible within an hour. But it's to highlight through their differences things that you need to think about, and ideas that you need to be aware of if you're to sensibly critique these things in future. So let's talk about why we'd use a broker-based messaging system in the first place. So if I have two systems hooked up into each other, they are separated away by an interface. Yeah, you agree on a contract between how these things are going to communicate. This is not complicated. We do this every single day. This is Computer Science 101. Yeah. So why would we introduce something in the middle? Well, it's to further separate the two systems. But what do you mean? You've kind of separated by interface. The implementation can change. Well, this is a different kind of separation. It's a separation over time. Consumers don't need to be there when a producer is sending a message in the first place. So this is analogous to a post office system. You send a parcel, the recipient doesn't actually need to be at home. As long as you've handed the parcel to the post office, they've given you a receipt, you trust that through the magic of modern delivery of parcels, it will eventually end up at its destination. So let's talk about ActiveMQ. What exactly are its goals? Well, firstly, its goal is to be a free open source software JMS messaging implementation. Okay? It is fundamentally a general purpose messaging broker, so it has a wide variety of use cases. And it's supposed to allow clients to interact via multiple protocols. So what exactly does this thing look like? Well, a broker here, messaging in general, actually has two sides to it. The first one is a server-side element, which is the broker, and then there is a client-side portion which deals with things like failover, etc., and the actual communication to the broker. In JMS terms, there is a standard API that you talk over, and your code sits over the top. The communication between the client and the broker is performed through the wire format. What is the wire format? Well, a wire format is simply an agreed protocol for a client and a broker to talk to each other. Okay, let's leave it at that. So what sorts of wire formats are available? Well, in ActiveMQ, you have one called OpenWire, which is specifically for ActiveMQ. JMS doesn't say anything about protocols. Yeah? In that respect, it's very much like a sausage. As long as it tastes good, just eat it. Don't worry too much about what's inside. You've also got AMQP 1.0, not to be confused with 0.9.1, which is a completely different thing in RabbitMQ. This is an industry standard protocol. You have Stomp, which is a text-based thing, which you can kind of communicate to it through many different kinds of languages, everything from Bash through to JavaScript, Python, whatever. MQTT for IoT applications. XMPP if you want to treat your message broker like a chat room. You can also talk about WebSockets, which is not bad for a humble little broker. So there are two messaging domains that a regular broker, a classic broker like ActiveMQ needs to deal with. The first was point-to-point or queues. Queues are a first-in, first-out data structure that is durable. If you've got no consumer, or receiver in this particular case, no problem. It kind of acts as a buffer. Okay? The messages that are actually sent into a queue are persisted if you want them to be. Durability is really just the quality of service, that if the consumer comes along later, it will receive any messages that were sent while it was gone. Durability doesn't equal persistence. Okay? Durability is a quality of service, whereas persistence is just, is this particular message written down to a disk? Can it survive the queue itself going down, or the broker itself going down? So this is the domain that we're mostly going to focus on today, simply because it's the one that we're most often interested in. There is another domain, which is topics, implemented through publish subscribe, which is non-durable. What does non-durable mean? Well, here it acts more like a conference call. So if you happen to be connected to a conference call, you hear everything that is being said from the producer. If your consumer disconnects, then it misses whatever was said on the conference call. So these can be made durable, so that a consumer will receive messages later. And durable subscriptions can also take advantage of persistence, but by default, they're not durable. So now that we've got some basic definitions, let's consider something that every single system that speaks over a network and writes to a disk has to kind of deal with. As what I refer to as the reliability versus performance trade-off. Okay? This is a spectrum that you can position an arrow on anywhere. Okay? If you want to make something more performant, it's going to be less reliable. So JMS default, this is what ActiveMQ actually works with, is to set the reliability all the way. But it is, of course, tunable. There's going to be animations in this presentation. So to understand brokers and this reliability performance trade-off, you need to understand how exactly they go about storing messages. So let's talk about journals. A journal is a persistent data structure made up of multiple files. Okay? It contains a history of interactions that you have with a particular broker. So in the case of ActiveMQ, it's storing messages and acknowledgements. So if the broker shuts down, it can actually get back to its current state when it comes back up simply by reading the journals. Okay? So how exactly do messages end up in a queue in the first place, and how do they make use of this journal? Well, this is a necessarily simplified, but a fairly decent working model. So you have an application thread that's kind of coming along. You're in your producer. You send a message to ActiveMQ. ActiveMQ will write it to storage, our journal here, and get some sort of confirmation back. Get to that in a second. Only once it's gotten this confirmation does it actually send an acknowledgement, at which point of time your thread can keep going. So you're actually suspended for this particular time gap over here on the left-hand side, while these I/O operations are actually happening. So the confirmation step is actually the slowest component of the entire interaction. But why do we need it? I've written something to disk. Why do I need to know whether it's actually gotten to disk? Once it's on disk, right? Wrong. Caches everywhere. So, when you write to a disk, the first place that you actually write to is an operating system buffer cache. If you're interested in reading up about this, there's only one place on the entire interweb that this is actually mentioned, and it is in the Postgres documentation in Chapter 31, Reliability. So the operating system buffer cache, it caches frequently read blocks, and it combines disk writes so that it's not constantly going down all the way through the I/O stack. Doing I/O is really, really, really expensive, and you want to avoid it as often as possible, unless you don't. So once let's say we've gotten through this operating system buffer cache, what's next? Well, we hit the disk drive controller cache, especially in RAID systems. You will find these things. Some of these are write through. Some of them are write behind, so I write into it and eventually it kind of flushes itself out, and they're usually volatile. Trip over the power cable, all of the stuff that's in there has just disappeared. But you thought it was written to disk, right? So let's say we've gotten through the disk drive controller cache. Where do we hit? Well, we hit the disk drive cache. Because there's a piece of memory on there, again, which is either write through or write behind. In consumer drives, which is actually what we tend to use most often, because they're actually more highly reliable than enterprise drives. Surprise, surprise. They usually write back, and again, they're volatile. Flick the power switch, everything just goes up in flames. There's all your writes that you've missed, which is incidentally, all of this stuff is why your operating system complains at you because you haven't ejected the USB drive. So most signals for all of this kind of buffer interaction are only available to the operating system. From Java, which is what ActiveMQ is written in, we have an operation called sync, which sends a POSIX signal called sync, which tells the operating system to go off and flush the buffers. Okay? So in ActiveMQ, the disk, the cost of this write through all of these buffers to get all the way through the hardware, our confirmation step, is actually the most expensive step. So before we go any further, let's talk a little bit about disks. Again, this is a simplified model that I've kind of made up. It kind of tends to work pretty well. So let's look at it. Think about writing to a disk as a pipe. All right. The length of the pipe will dictate the latency. So if I actually say I'd like to write something, how long is it actually going to take to write to disk? The next performance factor is the width of the pipe. What is the carrying capacity of every single operation that I send down this pipe? How wide is it? And what's more, how many things can I stick in this pipe over the course of a period of time. And that's defined by something called IOPS. Has anyone heard of IOPS? Yeah, some people who have heard of IOPS. Brilliant. So IOPS is a scam and a farce perpetrated on you by disk vendors, right? It is an approximate measurement with different meanings depending on context. A drive will have different IOPS numbers, and in reality, it will completely diverge with what's on the data set, on the description of this drive. So depending on whether you're doing just reads, or whether you're doing just writes, or whether you're doing a combination of reads and writes, and whether those reads and writes are sequential or random, you're going to get completely different numbers. And the block size, which is the carrying capacity, right? So the overall throughput of an I/O pipeline is going to be defined by the first of these limits to be hit. Okay, so we've said that in ActiveMQ this is, the main driver or the main limiter of performance, but it's not the only one, because we also have internal contention. So if we're trying to write to a file from multiple threads, from multiple producers that are putting in messages to different queues, at some point in time, you're going to have some sort of mutual exclusion mechanism in there to line up these writes behind each other. So this is there to ensure that the journals don't get corrupted. The upside of this design choice, to put all the message in the same journal, regardless of which queues they came in on, is that you can really straightforwardly implement transactions. Who likes transactions? Transactions are much better than that. Transactions are awesome. So one of the great things about transactions is that you can send messages to QA, QB, QC, and then send a commit operation. A commit operation is all or nothing. So you do one write, one confirmation. So now we're expanding to use the carrying capacity of the disk, and we're sending a bigger write once. This gives you orders of magnitude in performance improvement. This is brilliant, really, really good. So the other nice thing is, because you've got transactions, you can actually tie them into broader transaction management APIs. Things like JTA, for example, for XA transactions. So let's talk about queue consumption on the other hand. So a consumer comes along and subscribes. What exactly goes about happening? So ActiveMQ will page in a bunch of messages into memory and dispatch them over to the consumer. It keeps around a little area of memory that says, where have these messages gone to? Okay. The consumption is actually going to be out of this little buffer. It's called a prefetch buffer, and it's going to be processed. At some point in time, you're going to get an acknowledgement. The relationship between these two things depends on what's called an acknowledgement mode. Is this transacted? If so, acknowledgement is going to happen after consumption. If it's not, then the acknowledgement will happen as soon as you get consumed. Okay, that's called auto acknowledgement. Okay, only once ActiveMQ's gotten this acknowledgement will it actually go and delete the queue, the message out of the queue. Okay, in reality, it writes an acknowledgement into the journal and increments a pointer, and you kind of don't need to worry too much about that. So journals that have had all of the messages within them consumed, they eventually get deleted through a kind of a background cleaning process. Okay, so once a message has been consumed, it will not be consumed again. This is very, very important. So what happens if you've got multiple consumers? Well, if I've got a producer, I'm sending in a bunch of messages, they're going to be round-robined between the consumers that I currently have. If I add a third consumer, that's going to go into the round-robin cycle. So what happens if one of these nodes fails? I said that messages are being kept around on the broker. So what they're going to do is they're going to be redispatched over to another consumer that can then go about processing them. Okay? So this is a very simple consumption model in that clients only care about responding messages that they've received. Yeah, fairly straightforward. The broker is responsible for keeping track of the consumption and ensuring that these things will be delivered. It's very much like a post office. We don't know how the post office works. It just kind of works. It's an amazing thing. What's interesting in here, though, is actually the timing of the failure. Because if I've started consuming a message, I've called out to a web service, and then my system crashes, that same message will be delivered to another consumer, and that web service will be invoked again. because the broker has no idea about the actual processing of the message. It never got an acknowledgement, so it just redelivers. As long as it didn't get an ACK, it wasn't processed as far as it's concerned. So the best we can hope for here is at least once message delivery. Now this should put terror into your minds, because what it means is there's no such thing as once and only once, which is usually the way that people have mythologized the way that these things work. It has fundamental implications about the way that you need to think about message processing logic. So how exactly do we now guarantee that messages will still be delivered if we use, if the broker goes down? Well, ActiveMQ is a little bit old school. It works a bit like, it's analogous in messaging to, I suppose, a Postgres. It uses a master-slave-based system. So there is a shared piece of storage. The first ActiveMQ node in a pair will connect to it, and it'll say, right, I'm the master. I have exclusive access over this particular store. And the consumer has code in it that says, hey, to connect to the broker, you're either connecting over to host A or you're connecting over to host B. And so once host A opens its ports, it is the master. Our client can now connect into it. Our slave comes along. It's turned on a little bit later. It goes, can I get exclusive access to these journals? It goes, well, no, you can't. Someone else has got them at the moment. So it goes, okay, well, I'm just going to back off. And every once in a while, I'm just going to periodically check in and just say, hey, can I take over and can I be the master? Until that point in time, the ports are closed. So it's in a warm state with nothing able to actually to put messages or retrieve messages out of it. So here we've got two physical brokers that are acting as one logical broker. So what happens if aid goes down? Well, at this point in time, the master's been periodically checking the store and now goes, oh, I can get an access to it. It opens its port. The client, which has been rudely disconnected, now goes between checking, can I go connect to A? No. Can I connect to B? No. Can I connect to A? No. Oh, there's a port that's just opened up on B. I can now connect to B, and I continue from where I was. So it's a nice little mechanism. So in ActiveMQ, disk access matters. So aside from having to set up some sort of shared storage, disks, you need to ensure exclusive access for the ActiveMQ process. Okay? So that you don't get processes coming in on the side and using those same disks and causing contention. Because if we're relying on a disk to behave in a particular way and then someone runs a database report on a database that is sitting over those same disks, what's going to happen over our broker? It's going to rudely slow down. Yeah? So this is a massive problem in virtualized environments without something called storage affinity, which basically guarantees that a particular node will have exclusive access to a piece of the overall disk. So this guarantee of clear access to the disk is absolutely necessary. So one of the interesting implications of this is that this isn't actually a very good fit for containers. Why? Because you need a manual box setup. You care about where your disk is. You care about how it performs. You care that nothing else is interfering with it. Okay? In particular, you need to kind of watch out if you're using orchestration, because these things can't just run anywhere. Disk location matters. An interesting thing that I've been using as an example is Salesforce. Salesforce containerized everything except anything that talked to a disk, which meant no databases and no message brokers. Okay. So how do you scale this up and out? Well, the first thing is you can increase the disk speed. The faster the disk, the faster it'll go. ActiveMQ goes really, really, really fast when it doesn't have to talk to a disk. You can make better use of disk dimensions. So use transactions. By all means, get these writes to be much larger. Or alternatively, you can actually split the messaging over multiple brokers. Not everything has to go over the one broker. In fact, the use of everything over the one broker is what I refer to as the big bag of messaging, where you have system A, B, C, and D, and they all need to speak to each other, so you stick them all onto the same broker, where anything can talk to anything. Absolutely do not do this. This is a recipe for complete disaster. When an architect comes up with a diagram like this, they're thinking of ActiveMQ as a conceptual layer, not a piece of physical infrastructure. If I replaced ActiveMQ with Oracle, would this be the one database? Probably not. Would it be the same database server? Probably not. Yeah? Same thing in ActiveMQ. So a little bit of thought is required. So what exactly are the trade-offs? Because everything in engineering is trade-offs. So on the bright side, it's a simple model. A little bit too simple. I like to say that ActiveMQ is not like physics, because you can download ActiveMQ, install it on a server, and run it, and it'll run until it doesn't 6 months later. It's transactional, and it has a rich set of supporting functionality. So it has things like message routing and filtering, fairly rudimentary, but it works very well. There's a bit of wiretapping. It can do things like broker networks for geographical distribution across continents, across data centers, all sorts of interesting stuff like this. There are downsides, much like there are for any technology. The performance is pinned to your disks. Disk matters. The performance is also impacted by the total load on the broker. So if one queue is getting huge volumes of traffic and you're expecting a reliable kind of performance out of another queue, you may find that you're being interrupted. It requires non-transparent changes to the broker topology, so which systems use which broker over time. So what might cause a change like this? Well, you might get changing traffic volumes, an extra million messages a day. You might increase the number of total destinations, queues, topics that are being used, or the payload sizes might be different to what you originally expected or might grow over time. So in short, it requires that you have an understanding of the internal mechanics of how this tool works, and you need some upfront thought in order to get this right. Let's take a quick break. Stand up. Stand up, stand up, stand up, stand up. This is a long afternoon and this is a warm room. Now have a good stretch. Have a good stretch. That's it, yeah. Turn to the person next to you, shake their hand. Say hello, I hope you're enjoying the presentation. You can now sit down again. Okay. So let's talk a little bit about Apache Kafka. Here you thought, hey, I'm just going to go to like a little kind of comparison conversation. I didn't expect to be talking about IOPS and disk sizes and contention and all of this sort of stuff. So sorry to disappoint. So let's talk about Kafka. So Kafka comes from a completely different philosophy and a completely different set of use cases. So it was designed at LinkedIn to get around the problem of multiple separate data feeds. Now, I believe the last presentation was kind of talking about Lambda architecture, is about messaging from kind of point to point. There's also some batch operations, that sort of thing. So LinkedIn had masses of these sorts of kind of point-to-point links, and it was all a bit of a mess. And what they wanted from Kafka was they wanted to address some of the shortcomings of ActiveMQ. So primarily the one about needing to set up different brokers in slightly different configurations for slightly different pipelines and data needs. So the initial use cases around it were for things like moving logs, notification of UI events, monitoring events, that sort of thing. So what were some of its goals? Be fast. Oh my goodness, is Kafka fast. Kafka does persistent messaging faster than a disk can write it. That's fast. It also means there is trickery. It handles huge volumes of messages. Don't have enough messages? No worries. Chuck on an extra broker. It will fly and it will just laugh at you. It scales horizontally. It needs to support publish, subscribe, as well as point-to-point. And it needs to allow the no-cost addition of consumers. You want to add an additional consumer? No worries. Kafka will perform exactly the same way for all the other consumers. That's crazy. Not only that, it also permits you to do replays. Remember in ActiveMQ when we sent a message, we couldn't play it back. That message had already been deleted. Kafka, completely different way of working. So how does it do this? Well, first of all, Kafka doesn't have queues and topics in the same way. It has a unified destination model, which I'm going to refer to as a Kafka topic, to be different from just a topic. A Kafka topic is both a queue and a topic at the same time. Whoa. It contains, conceptually, one journal with multiple pointers to internal locations. So what exactly are these pointers? Well, that's not the real name of these things. If you look at them in the documentation, it's really my way of conceptualizing it. A pointer is an offset position in a log file, a journal, that is associated with a consumer group. So what is this consumer group? Well, a consumer group is a label which corresponds to a single logical consumer. And a logical consumer in this case means a system, a particular system, not an instance of a system, a whole system. In code, it's referred to by a group ID. So let's take a look at the mechanics of a Kafka topic. So we have a journal with some messages that have been written into it. So allowing multiple pointers means that a Kafka topic acts like a queue when only one system exists, or a topic when multiple systems exist. This is amazing. So let's talk about the multiplicity of this. Well, if I have one pointer and one consumer, as you would expect, the consumer gets all of the messages. Now, what if I have two instances of this particular system? So I've got two consumers using the one pointer. Well, the second consumer to come around gets all the messages. At this point in time, you're going, wait, hang on a second. That's a bit odd. So the new consumer takes over the message flow. Okay. This is a bit like a consumer priority feature where the newest consumer to come around will actually take all of the messages because it has the highest priority. This is really confusing for newcomers because it's completely different from the way that a regular JMS queue works. With a regular queue, if you've got two consumers, they'll share the load. With Kafka topic, not so much. So what about if you want to actually have multiple threads consuming the messages? Well, how do you go about doing this? Well, the Kafka docs suggest that if you want to process messages in parallel, you might want to do some multiplexing, okay? Where you have a number of threads that actually do processing, and you have one consumer in the machine instance that is actually pulling the messages off the broker. So only certain use cases allow for this, because if this machine instance fails, what happens to any messages that were in flight? No idea. So there's another option that Kafka gives you, and that's through the use of partitioning. Partitioning is also referred to and can be thought of as shards. So here, the messages for a single topic are split over multiple journals. Okay? These journals are referred to as partitions. So what happens if I have two instances of a system? They both get assigned one partition each. So I've got one topic, two partitions, two consumers. So each consumer here will receive messages from its partition. You'll see that the actual cursor, the pointer, refers to the same group ID. Okay, so each consumer instance controls its pointer in its named partition. Everyone with me? You're about 30 seconds ahead. So, consuming partitions. So what happens if I've got less consumers than I have partitions? Well, if you've got one consumer with multiple partitions, it'll consume from both. So it'll read messages from one, then it'll read messages from the other. So how exactly does this partitioning go about happening? Well, unlike ActiveMQ, where if you want partitioning and you want to split it over multiple brokers, you've kind of got to do it at the application level. In Kafka, it's built in, sort of. So partitioning, to understand it, you have to understand that it's performed by the producer. So the producer decides where to send the message. Before I get into the details of it, let's consider what exactly it is that we're sending. So a message here, in Kafka terms, a message is a key and a value. It's completely different from regular messaging, where you've got a payload with some headers and a body, and you just send that. No, key and a value. So what exactly is the key? We can probably guess that the value is the payload. Well, a key is a business-specific grouping used for partitioning, and it corresponds to a set of messages that should be processed in order by a single consumer. So a key might be something like an account number or a geographical location. Okay? As I said, the value is the payload. So in order to work out where you're going to partition to, you actually need to provide a partitioning function, which says, given the message and the current cluster state around the topic, give me the partition ID. Like, whoa, what is this? So it's actually not as horrific as it sounds. So you've got this interface, which gets given the name of a string, a key and a value as an object. You got the byte equivalent of it if you want to look at it, and then you've got the current cluster state, and you've got to implement it yourself. So the default implementation for this uses a hash function. Now, this has a kind of a weird effect because you get an uneven distribution across partitions. So some partitions get loads of messages, other partitions get very few messages. Why is this? Well, firstly, you get skews in your keys. So some keys have many more messages. And the other one is that if you've got a small number of partitions, then you get hash collisions as well. Yeah. So what are some of the partitioning considerations that you need to do if you're going to implement? I'll ask questions afterwards, okay? So some of the things that you need to think of if you don't like this particular scheme, well, you need to ensure that all related messages end up on the same partition. Yeah? It seems like a fairly reasonable thing. You need to ensure some sort of an evenness of distribution, because you can't have some machines in your cluster just dying under the weight of the message flow while others are kind of merrily treading along. And then you need some sort of a stickiness to a key to a partition. So Kafka actually allows you to add partitions to a Kafka topic at runtime. So the actual cluster state can change over time. So to make sure that messages that need to be processed after each other actually get processed after each other, you need to ensure that even if they were to go to a different partition, they still go to the old partition. So this is actually pretty complicated. Because if you've got some sort of a state around, like, okay, these messages must end up going to this particular partition, and you've got multiple producers, producer might be a web server in this particular case, then those producers need to share that state. So you need something like an in-memory data grid or something like that to actually keep that state around. So it's now we're starting to get a little bit wacky. So now you're kind of thinking, why? Why this is so complicated? Well, it's to support a fair distribution of messages to multiple consumers without incurring the cost of managing the dispatch. So what Kafka's done is it's rephrased the distribution dispatch problem to one of partitioning. Okay? And it's moved the responsibility for the fair distribution of messages back to the producer, which means your code. So your code is now taking on some of the functions of a regular message broker. Okay? Thankfully, that's it in terms of complexity, right? No. We wish. So one of the things is, if you're trying to send something, you send a key and a value, it's called a producer record, and you get a future. Uh-oh. The future isn't now. What you're actually doing is your thread's coming along and it's sending really, really fast to a buffer inside the same library, which is then talking over to the Kafka broker. Okay, so if you've got a number of messages in this buffer and the sending system goes down, can you replay? Do you know that you need to replay? Well, at least it's fast. Well, we can kind of tune it to be much more reliable by kind of setting the buffer size to be 0. We can make the call synchronous. We can wait on the future. And that's okay. That kind of deals with the sending side. And that's all we have to worry about, right? No, it's trick questions all the way down. To consume messages, there's also a little bit of additional complexity. Well, to fetch messages, you poll for them with a timeout, and it gives you consumer records, plural. Okay? So you're receiving multiple messages within a single poll operation. So what exactly happens during a poll? So here's our initial offset at the very beginning of the journal. The consumer comes along and gets some messages fed to it. At some point, the offset is automatically incremented, but that's got nothing to do with the consumption of the messages. Because the new location of the pointer, or more correctly the offset, is typically auto-committed. And it's not tied to whether or not the message has been processed at all. So a crash means that you get a loss of knowledge about any messages that were in flight. They haven't actually been processed, but the pointer has moved on. So when another consumer takes over, it takes over from the new offset. And it has no idea that the previous messages weren't consumed. Which leads us to a horrific conclusion that consumption is non-transactional by default. So how would you get around this? Well, there's a setting inside the consumer config where you say, I want to disable auto-commit. Then I want to commit manually, which I've got a couple of different options. I can commit or I can commit sync. Yeah, if I'm consuming a group of messages, I can also say, I just want one message every time I poll. But that slows you right down. Yeah? You're no longer getting a batch of messages, you're just getting one message. So every single time you're going to have to go backwards and forwards to Kafka, so you're slowing yourself down. Now, the interesting thing about this is that while you've got a commit, Kafka has no concept of rollback. There's no transaction here. It's only pseudo-transactional, so you've got to deal with this yourself. So you can potentially rewind stuff, rewind cursors, etc. So one of the alternative things is that you can keep track of the messages that have been processed, and when you get a partition assignment event, this is something that happens in a consumer, you can register a listener, you rewind the offset all the way to the beginning. And then you just reprocess every single message and discard the ones that you've seen previously. This is something that's known as an idempotent consumer. Alternatively, you can keep the consumer code simple and use it when some sort of message loss is acceptable, which is the original use cases that Kafka was originally designed for. Kafka wasn't designed for you to take actions on like $10 million trades, right? It's designed for moving of log files and pointer events. This is the A10 Thunderbolt, also known as the Warthog. It is the most survivable plane ever built. It is designed for close air support, tanks, vehicles, ground targets. It is designed to fly with one engine, one tail, one elevator, and half a wing missing. It can also survive direct 23mm anti-aircraft fire and keep the pilot perfectly safe. Kafka's a lot like the Warthog. With Kafka clusters, one of the nodes in the Kafka cluster is marked as a leader. This is completely different to ActiveMQ, which had a kind of a traditional master-slave shared storage mechanism. Kafka's been designed to be cloud first, to run on simple commodity hardware. It is the NoSQL of messaging, right? So each Kafka topic partition to be more correct, has a leader, which is a master, and followers, which are kind of like slaves, with some sort of replication bits going on between them. So by keeping track of which which of these replicas are actually in sync, you can actually tolerate all but one node's failing. Yeah. So all the reads and writes going into a topic actually go through the leader. The client sets up how many commit responses they actually want back. Again, it's performance versus reliability. Kafka's got a multi-leader architecture in that every single node can be a leader at the same time. Because within these groupings, a Kafka instance can be leader for one partition. So here you've got Kafka 1 being a leader for the red partition. And here you've got Kafka 2 being a leader for the blue partition while also being a follower for the red one. The coordination of who is actually the leader and who is the follower and who's currently in sync, etc., is performed by Zookeeper. So Zookeeper is keeping track of the present broker nodes, the topics and partitions that are currently being maintained, who's the leader, who's the follower, which consumers exist and which consumer groups there are. The interesting thing was that journal offsets were also originally stored in Zookeeper. And that's actually been reworked so that now journal offsets are maintained inside Kafka on another topic. Simply because Zookeeper wasn't fast enough to keep up with acknowledgements coming back from clients. So the implications of this entire architecture is that you have no need for shared hardware or storage, because the replication is actually being done at the broker level. Through the replication of leaders and followers, you don't even need to sync in through to a disk. This means that you get up to 3 orders of magnitude higher performance per node than a regular broker. If you take disk out of the equation, my lord, can it fly. It's amazing. So the trade-offs on this is that it's actually really, really, really easy to scale. If you've got a cluster, it's not going fast enough, chuck in more nodes. You have a high throughput due to the resiliency design. Because I don't need to write something to a disk, don't write it to a disk. Don't flush the disk. In fact, what it's doing is messages are still getting written to a disk, but they're only hitting the operating system buffer. And through the magic of zero copy reads, which you can look up if you really want to, the actual handoff of messaging is insanely fast, which leads it to work really, really well for low latency applications. Furthermore, it's very easy to run on commodity hardware. There's nothing specialized that you need to buy for this at all. So as I said, everything is an engineering trade-off, right? So there are always downsides. It's not transactional. Not really. If you do need transactionality, well, there's lots of client complexity that needs to be re-implemented across systems and languages. Who here works in an organization that works in a pure Java stack? There's like one person, right? For the rest of us, there's a bit of Python, there's a bit of Ruby, there might be some Go, there might be some random things. Yeah? All of that logic needs to be re-implemented. And finally, you need an understanding of the internal mechanics and upfront thought to get right. And if you've been paying attention, I also said this about ActiveMQ. There's no magic going on here. So what works for you? Well, you might want to use ActiveMQ when you have high individual value messages. You care about not missing messages and you want them processed in order. Kafka doesn't actually lose messages. You might just not receive them. There's a difference. It supports non-durable public subscribe. Not everything needs to be written to a disk. Yeah. You can also use a broker as a transport bridge. So I've got a JavaScript client running in a browser talking over WebSockets, talking to a broker, which is then having the messages consumed by a C++ client talking in AMQP. So it's acting as a protocol converter. You can also do request reply over messaging. Kafka doesn't have the idea of metadata, so it can't correlate messages back with each other. And it also has some simple message routing. Also, you can span geographical locations really, really straightforwardly. There's some nice there's some copying mechanisms inside Kafka as well. It kind of sits as a separate process, but there's some complexities around that, as you can imagine. So when would you need to use Kafka? So you'd use it when you have messaging that is valuable in aggregate. The more messaging you have, this is a personal observation, the more messaging you have, the less value an individual message has. So this is for things like user activities, log aggregation, UI performance, diagnostic events, clicks. If you're doing this sort of stuff, then probably you have a huge throughput of data. So if you're looking to be sending in the tens of thousands or hundreds of thousands or millions of things a second, Kafka is probably for you. Alternatively, there's a new kind of application model called event sourcing, where the entire state of a node can be rebuilt by playing back all of the events that have come through in the past. So because Kafka supports the replay of messages through the rewinding of cursors, you can implement that very, very easily using this as a store. So to conclude, horses don't fly. There's nothing mystical about messaging. So neither platform gives you everything, meaning transactionality, consumer failure awareness, effortless scalability, storage transparency, drop and go in production. They have different use cases and take different trade-offs. Having said that, use the right tool for the job. You could, of course, use both, and this is what happens at a large number of companies. Your architecture will probably skew one way or the other, though. NoSQL didn't replace relational databases. It rather filled niches. Graph, document databases, all of these things have their own place. In the same way, Kafka offers an alternative complementary tool set to traditional messaging to address a different set of use cases. So regardless of which tools you end up using, invest the time to understand them. They are, after all, a foundation for the remainder of your architecture and will define what the architectural trade-offs actually are, and use the right tool when it makes sense. In short, more logos, less mythos. My name is Jakub Korab. Thank you very much. Can you microphone, please? There we go. We're just trying to get a power button going.
Okay, try now. What's about ordering of messages between partitions?
There is none.
So if I want strict ordering and I have a bunch of data or messages, I need to stick to a single partition.
No. Your partitioning algorithm has to hash them into the same places. So if you're using the default partitioning algorithm, they all need to use the same key. So for example, if I'm sending financial transactions from a bank, right? The first thing will be set up a bank account. The second one is deposit some money in the bank account. The third one is withdraw money in the bank account. You don't want these things processed in order because that doesn't make any sense. So what exactly is the key to the partitioning scheme in that particular case? An account number. Yeah. So all of the messages for that particular account number will end up in the same partition. Okay? So this is what I meant, that the keys to the actual partitioning algorithm are business specific depending on what it is that you're actually trying to send and how those messages need to be processed relative to each other.
And what is the default hash function?
There's a 3-letter acronym for it.
MD5?
No. It's something else. It gives consistent hashing across a very large set. So you can take a look at that if you want. The code's all open source.
Thanks.
And it's all very straightforward. Thank you. Any other questions? Yeah, sure. The gentleman in the checkered shirt.
You said that for the ActiveMQ we need the dedicated hardware.
Yes.
If we have multiple instances which are using some virtualization and which are in different server, how they are sharing the same hardware?
Okay, so that's an excellent question. What you normally do is you actually have 3 boxes. Logically, you have 3 boxes. The first one is a machine instance that runs one ActiveMQ instance. The second one runs another ActiveMQ instance, and they talk to a third thing with a network file system, typically. Okay, so usually something like NTFS4, right? Oh, sorry, NFS4, not NTFS. Don't use NTFS. Smelly, super smelly. Don't ever touch it. And so this other thing could be some sort of a storage array. There's different ways to set that up, usually involving tricks like heartbeat and distributed reliable block device and all kinds of crazy operating system type processes. Alternatively, you could use things like shared file systems as well, so that the shared file system is actually virtual. So Gluster is particularly good. You could probably also use Ceph for this as well. Both of them are open source, they're supported by Red Hat. One of the things you should not use under any circumstances is a SAN, right? Do not ever use a SAN. Oh my lord, SANs were like sold by like EMC and stuff like that. They are completely unsuitable for this. If you see the people from Cassandra talking about, you know, the worst thing that you could possibly do to set up Cassandra, run it on a SAN. Don't run it on a SAN. No. The problem with it is actually the disk contention, right? Because you can't guarantee that only your process has control over a single disk. And I've used the example of a database which is running, and someone's running a database report, a monthly report, during a high volume part of the day where you're getting a lot of messaging and everything just kind of grinds to a halt, and everyone points their finger at ActiveMQ, which is just doing what it's supposed to do. It's just that the storage has started to go really, really slowly. Yeah. So this is one of the things that I get called in for really, really frequently about, you know, how do you actually go about setting these things up? What exactly are the trade-offs and that sort of thing? So there's a lot of options there and a lot of different ways of approaching it, depending on your particular use cases. Yeah.
Thank you.
No worries. Sure.
Thank you. Hi, I have a very particular question.
Oh.
In our setup, we are having ActiveMQs that are fetching statistical messages, and we have some kind of consumers that fetch them in the batches, and this is something that is done regularly. I think 20 minutes or something like that. And what do you think about using local storages and also master-slave? For example, you have a broker that goes to one or the second ActiveMQ, it uses local storage, and every 20 minutes something consumes that messages, and they are coming down to some kind of a database. And it's a statistical kind of messages, or
okay. So
Kafka would definitely...
The question's actually a red herring. Yeah. So the thing here is, the key part of your question is, I have statistical messages. I don't care if I lose these messages. Do I need a shared file system?
Yeah.
No, you don't. Because the only thing that persistence is actually there for is to make sure that when the broker comes back up, it has all of the messages that were there beforehand. Now, if you don't care about losing messages, if your hard disk catches on fire, right, or squirrels cause a short circuit, right, which is a great little image, squirrel going, then if you lose the disk, you don't care, because the data wasn't that valuable to begin with, which raises an interesting question. Why are you putting it to disk in the first place? Yeah? So one of the things that you could potentially do is actually just give a broker a huge amount of memory and mark the messages as being non-persistent. So you get a much, much, much higher throughput without having to go anywhere near a disk. And then you can actually stick it into a container. You can stick it into a Docker container because you don't care about the storage, right?
Yeah, because we are implementing some other solution, and we're trying to find a way to optimize it. That's the problem. Perfect. But you would definitely, in that case, you said that Kafka is great for messaging in aggregates, and I think that statistics is something.
Yeah, but
when you
again,
don't need to know person who did something, but you need to know that something has 1 million visits and things.
All
like
of these things are trade-offs.
Yeah.
Right. So I say messaging that's valuable in aggregate, if you have enough messages there. Yeah. So ActiveMQ will laugh at you if you're sending non-persistent messages in terms of volumes. Like if you're sending any less than 30,000 messages a second, ActiveMQ will just go, yeah, fine, whatever, no worries. 30,000 messages a second is a lot of messages, right? If you're talking about, I want to send 1 million messages a second, then go for Kafka, right? Why? Because so try to get the most out of one broker before you go to many brokers. Distributed systems are really, really hard, and they come with a lot of complexity for the initial setup time, as well as for just the operational cost of running them. So one thing is better than many things. No things are even better than one thing, right? So you might even go for something like a 0MQ, which doesn't even need an intermediary, right? So there's many different kinds of messaging products that support different kinds of use cases, which all have different trade-offs, right? So I want you, through what I've said in this particular presentation, to just be able to reason about this stuff. Do I need to send it? Do I need to persist this message at all? If I don't need to send it, I don't need to send it to disk. Yeah. Can I do it over one node? No, I can't do it over one node. I need many nodes. How many nodes? Then you can start thinking about it from that point of view.
Okay, thank you.
No worries. Any other questions? No? Excellent. Thank you very much. Remember, vote 5 for technical presentations. Thank you.